Welcome to the next session of Embedded Software Testing Unit 2, the testing methods, lecture 14. This is an important unit because based on this, the entire embedded software testing lies. So we will be doing a detailed understanding and detailed examples through of different testing methods. It is very important to understand the testing methods like what we spoke about black box testing and different design techniques or selection techniques of black box testing. Today we will study the boundary value analysis. This is again a design technique, test selection criteria technique. Again for this the platform is equivalence partitioning. What are the fundamentals that we had understood in equivalence partitioning? Same thing also. Exception being some of the values we consider differently. Okay, so before that we will just have a glance of what we studied in equivalence partitioning. Equivalence partitioning we know why we need, because we cannot afford to have numerous test cases simply because we have a possibility of doing tests with a different number of inputs, because the system can behave either a normal way or an abnormal way. For a typical requirement, we need to test only the sufficient levels of inputs. How we can do that reduction is by having the partitioning, that is called equivalence partitioning. Also we understood that the basic purpose is to reduce the total number of test cases by partitioning the input conditions into finite number of equivalence classes. So we also studied about the first level of valid and invalid test cases. First we are going to define all the test cases, then we are going to have a partition of one usual behavior, what is expected for testing those inputs. Those are called valid equivalence partitioning. The other one which is other than the normal behavior in terms of the outside the count or whatever it is, those are all called invalid partition. And we define the numbers accordingly, equivalent valid 1, valid 2, valid 3 based on the classes, and each class will have at least one test case selected from. And we also studied an example of integer n ranging from minus 19 to 99 to plus 99. So valid equivalence class will have minus 10, minus 9, minus 1. So like this we have about 5 valid equivalence classes. Similarly we have about 3 to 4 invalid equivalence classes where we are trying to input the values such a way that it is tested with an invalid range of inputs. Similarly, another example of phone number we had studied, and also we understood about guidelines. There are about 3, 4, 5 guidelines that are important in terms of time, memory, size, range, count, etc. We took a few more examples in terms of temperature from 15 to 40. Then we have fuel level sensors having 3 types of indicators: yellow, red, green. So we know that what is invalid, what is valid. So basically we are going to draw a range of all the test cases, and against the range we are going to create a table. It's called a truth table, having all the possible combinations defined for each of that inputs with the help of different columns. And further we are going to have the equivalence classes divided as valid and invalid as per the below table. We also know that we can have the output equivalence classes if defined as well, not only the input equivalence. So that is about equivalence partition. But today we will go through the black box testing technique called boundary value analysis. So what is a boundary value analysis? First we understood that the equivalence partitioning is done with the help of valid and invalid classes, where valid will have the numerous number of test cases. You can see that black dots within the first pie, and the second pie has invalid test cases, and the further we are going to group them in terms of say this is one set, this is another set, this is another set. So like this we have, say for valid some 4 are there, for invalid there are equivalence valid 1, then we have equivalence valid 2, then equivalence valid 3, etc. Similarly we have equivalence invalid 1, we have equivalence invalid 2, so equivalence invalid 3. Here we have equivalence valid 4. There are 4 valid equivalence classes and 3 invalid equivalence classes. So out of this group of valid classes, we can select any one which is appropriate for that particular system which is under test, or that particular requirement which is under test. Now again we might have one or more covering within the equivalence class. It is very important for us to understand the typical requirement behavior also, because we need to see most of the requirements lying with a bounded values, right, like A and B. So surrounding A and surrounding B, how we are going to test it, that also we need to consider, which is nothing but the boundary value which will be subject to test. So continuation of the same equivalence partitioning. Here we have a boundary value analysis. So we choose a selection. This is what we have done of each group of equivalence classes, valid or invalid. One test case we have selected. You can see that round marked ones as the chosen test cases. So if an input condition specifies a range bounded by values A and B, test cases should be designed with value A and B, and also just above A and just below B, and just like this we are going to have it. So the next slide. So you can see there is a boundary of A just above A and just above B. Suppose the dot that is lying on the boundary, we need to test with a value which is just above A, just below A. This is for the first equivalence class. Similarly for our equivalence class we need to have it. Similarly for invalid classes also we need to have it the same way. So which is nothing but the boundary value analysis. So the first step is create test cases to test boundaries of equivalence classes. For each identified boundary in input and output, create 2 test cases. That means we know that 2 dots are here, right, for the boundary conditions. 2 test cases definitely are going to be there. One test case on each side of the boundary, but both as close as possible to the actual boundary line. That means how the system behaves for that boundary inputs. One for the low, one for the high, or it could be one for the negative, the other one could be for positive, or one for the below, another one for the above. So likewise we are going to have boundary values defined. So I will repeat again. We have a valid and invalid classes partition defined. We are going to define them as equivalence classes valid and invalid. We have a selection criteria within that each. One good test selection we are going to have it within the valid and invalid classes. Once we have that, we are going to add further for the requirement which are lying with the bounded values with the help of this boundary inputs and outputs. You can see for each of the equivalence classes valid and invalid we have a boundary conditions defined. Okay. Okay, the next one is the test cases made by boundary value analysis will catch more types of errors. You know why? Because the system behavior of the boundary could change. Suppose the system is supposed to take a variable of 1.0 to 5.0 and we are trying to test 0.9 or we are trying to test 4.9 or 5.1. The system should behave exactly. So we should be predictable basically. The chance of catching errors or issues at the boundary is more actually. That is why we need to have a boundary value analysis. But the disadvantage is that we will have more test cases. On the other hand, there will be more test cases which is more time consuming. Definitely it is time consuming because we need to identify for each of the boundary conditions. But it's equally important to identify the BVA, the boundary value analysis test cases. If you do boundaries only, you have covered all the partitions as well. That means definitely it is going to cover all the partitions. But better to have an intermediate value along with the boundary conditions. But what is said here is technically correct and maybe okay if everything works correctly. If the boundaries only are selected. So better to the best practice is to have an intermediate value along with the boundary. That means you have 1 to 10 as a requirement input. It is good to have a boundary value analysis for 1 and 10 and an intermediate value such as 5. So how many test cases we will have? For 1 we have a upper boundary and lower boundary as two test cases. For 10 we have a upper boundary and lower boundary as 9 and 11, 2 more test cases, it will become 4, then an intermediate value that is nothing but the fifth one. So totally 5 test cases for 1 to 10. If the test fails, it is the whole partition is wrong. It is not the test outcome or the test result. It is the test entire test what we are trying to do within that partition. If that fails, that means there is a problem with that partition or is a boundary in the wrong place. Have to test mid partition anyway. Testing only extremes may not give confidence for typical use scenarios, especially for users. As I said, we need to have an intermediate value, a good value like 5 when you consider ranges 1 to 10. Usually the system works from 1 to 10, like 2 it could be 3 or 5, 6, whatever it is. So better to identify one intermediate value. A good example is we know the car speed is 0 to 120, but there are less chances that the driver always drives at a 0 speed, or there is very few seconds that driver drives more than 150 or 200 kilometers. So trying it or testing it once at that boundary conditions is good, but it's very important that system is stable or the car is stable when it's driving in the range around 40 to 60 kilometers. So that is what it is called as normal test scenarios. that really gives a good confidence about the particular test. Sometimes it may be difficult to set the boundaries. Why? Because we know that car speed is 0 to 50, but going by the theory, we may not be able to test it less than 0, right? So how will you going to feed it? So are you going to take it reverse? It will definitely not show as -5 or -10 for sure, but we should have some simulation or some mechanism which is going to be costlier. Why we need it is we need to test it in terms of theoretically the requirements, whether it is collapsing or failing if the speed is less than 0, or likewise, or the RPM. It could be, it may not be speed, it could be engine RPM which goes beyond certain level. What is the behavior of that? So likewise we need to have a testing, but to test that it may be bit challenging in terms of setting up the environment. So we need to plan it appropriately. So basically boundary value analysis is a refinement of equivalence class partitioning. Instead of choosing any representative of each equivalence class, the main interest is focused on the boundaries for each of the class. The idea is to select one test case for each boundary of the equivalence class. The properties of a test case is this that belongs to a defined equivalence class and that it tests a value that it is preferable on. That means uh, one good value we need to select out of that class, or at least reasonably close to the boundary of that particular equivalent class. So the main reason why boundaries are important is that they are generally used by programmers to control the execution of the program, right? So programmers or the implementer would have implemented the boundary values as a boundary conditions such as less than, greater than, equal to, etc. So if that is let's say RPM is 6000 to 7200, definitely he has considered the lowest value as well as the highest value while implementing the code. So that is why we need to have the boundary value analysis. So to control the execution, the coder or the implementer would have had this control of execution based on these values. Definitely we will have for implementing this if then case statements, etc. So all this will be exercised of boundary value analysis. So while doing this, it is bound to happen that he could have implemented wrongly, or he would have made some mistakes while implementing. So we will study that what are those implementation issues in the next slides. And not that every one we tested twice, since there are two different equivalence classes on the two sides of the border, and there will be test for the boundary in both these equivalence classes. Means coverage is measured by dividing the number of executed test cases. So all these aspects we need to consider. Okay. So in other terms, we will detail out equivalence or boundary value analysis. The idea behind this principle is that defects can be caused by simple programming errors related to erroneous use of boundaries. As I said, less than, greater than, etc. So typically, the programmer has coded a less than, or when less than or equal should have been coded. When determining the test cases, values around these boundaries are chosen so that each boundary is tested with a minimum of two test cases. That means the lower one, the upper one. One which the input value is equal to the boundary, the one that is just beyond it. So this way we are going to design the test so that it will identify the underneath issues of implementation. So example, let's see, if a requirement says A less than B and in code it is implemented as A less than or equal to B, then detection possibility is more with BVA than EP. BVA means boundary value analysis, EP is equivalence partitioning. So this will bring out the issue of the boundary values when the implementer has implemented wrongly as against A less than B, like A less than or equal to B. One more example, if A less than B is implemented wrongly as A greater than B, this is also typically wrong. Then both EP and BVA could detect the error because this, the whole purpose of test itself will collapse here. So definitely in any of the tests, definitely is going to be caught. The above one still it is a valid, but equal to condition lies for the boundary, so it will be caught in the BVA, the boundary value analysis. And EP we would not have listed that particular test scenario for the equal condition. So going by the earlier example, what we discussed in the previous session, 15 less than or equal to temperature which is greater than which is less than or equal to 40. It means temperature lies between 15 and 40. It also includes 15 as well as 40, including 15 and 40. And assuming a tolerance of 0.1 in the temperature values, the boundary values to be selected are 14.9, 15, 40, and 40.1. So these are the equivalence classes along with the boundary value analysis. So what are those? Invalid equivalence classes. Here we have 14.9 as invalid, 40.1 as invalid, 15 is a normal, 40 is a valid because equal is there. Had equal not been there, then we would have had a valid class as 39. So suppose there is no equal to, then instead of 15 we should have had a 14 as a valid equivalence class. Similarly, if there was no equal for less than 40, then 39 would have been a valid equivalence class. 40 would have been a invalid equivalence class. And of course we have a tolerance of 0.1. Definitely in terms of boundary we need to have the 0.1 is considered the lower side after applying into the 15. We can have as well 15.1, here 39.9, right. So these are some of the valid and invalid equivalence classes and the boundary value analysis. So these two techniques are very important in terms of designing the tests. Boundary value analysis is a refinement of equivalence class partitioning. We know instead of choosing and representing from each equivalence class, interest is focused around the boundaries. So that is the main thing about this. Okay. So that is about boundary value analysis. As an example of temperature. Let's look into some more example. The same example what we had during equivalence partitioning. N digit can take an input from -99 to +99. What are the boundary cases? Here there is no question of valid and invalid equivalence classes. So that all will have it, but out of which the boundary cases we have to select it as a valid or invalid equivalence class. So let's focus only on the boundary cases. So what is the boundary case for minus n less than or equal to n is less than or equal to 99. So here are the boundary cases that we can have: minus 100, minus 99, minus 98. Of course, minus 99 as well is a boundary case because it is on the exact edge of the lower boundary. Similarly, we have minus 10 and minus 9, minus 1, 0, 1, 9 and 10, 98, 99, 100. So these intermediate values also we need to consider because these are all valid equivalence classes range. So we need to have this along with the boundary cases. Example, the next example is about phone number what we have seen earlier. So we will have boundary cases such as area code with 199, 200, 201 at the lower boundary, and at the higher boundary 998, 999 and 1000. For the prefix we know that 200, 199, 198 as the boundary, and the prefix at the higher boundary is with 998, 999 and 1000. And we have suffix any 4 digits, so we should have 3 digits as an input one suffix and 5 digits as another input suffix. So these are all some of the valid equivalence classes with boundary conditions which are allowed to test it. So it's a very important aspect of boundary value analysis. Okay, so we have gone through the example. In general, application of boundary value analysis can be done in uniform manner. That means uniformly we can select based on the input what the requirement is. Suppose if the requirement is a bit complicated, having numerous inputs and outputs, then better to have a defined truth table. So suggested to have a truth table identifying all the combinations. First identify all the combinations, then this is the first step. The next step is to go for identifying the boundary value analysis along with the equivalence partitioning, or equivalence partitioning you define first, then eliminate or add or complement to the equivalence partitioning with boundary conditions. So that is what should be the general behavior. This is especially important for complex requirements. So we know that we are going to address first the requirements, each requirements, how it can be tested. If that requirement needs another requirement to support, we may group that. We know that how the grouping can be done, that we have seen in our unit 1 sessions. The basic form of implementation is to maintain all but one of the variables at their nominal values and allowing the remaining variable to take on its extreme value. That means nominal, normal or average value first we have to select, then allowing the remaining variable to take as extreme values. The values used to test the extremities are the below. That means as we have seen in the previous example, to be precise on this selection, we are going to have first the log or complex requirements, these type of extremities. So we are going to have a minimal, we are going to have a minimal, little more than that, just above minimum, then nominal, nominal is nothing but average or normal, then we have a maximum value, then a maximum value little less than that, just below maximum. So this is the extremities we are going to consider for arriving at forming the boundary value analysis. So this is very important to have it. This is one of the definitions that is used in this reference from one of the education institute. Okay, boundary value analysis has a couple of very important aspects. Two we will discuss. The next date problem. The next date problem is a function of three variables: day, month, and year. Upon the input of certain date, it returns the date of the day after that of the input. The input variables have the obvious conditions like below. Day should be 1 to 31, month should be 1 to 12, and year should be 1812 to 2012. So this is the definition of three variables. We know these are all some of the realistic date. Similarly, we have for clock also we can do. So what is that next date problem we have to have? Here the year has been restricted so that the test cases are not too large. Why? Because we know that the system can take up to 2012. So there are more complicated issues to consider due to the dependencies between variables. That means these variables are very important so that dependencies have to be considered. For example, there is never a 31st of April. That means if we define this dependency of the date based on the month, correct? No? If you have a February or if you have a month, so we are not going to have a 31 as an input, right? So we cannot have a test case identifying a 31 for the month of April or for the month of February or any of the even months. So no matter what year is whereas day and month are dependent. So the nature of these dependencies is the reason this example is so useful to us. All errors in the next date problem are denoted by invalid input date. So very important thing also we need to understand is that we should be aware of the system requirements or user requirements or any what is it called, realistic inputs. Why this is important is one value is dependent on the other one. Here we know the month is dependent on the day. So the system which takes this way of input, it doesn't matter what year you have to feed. If you feed a month as April, April cannot have a day as 31. So we cannot have a day as 31 in case of February or April, etc. So we need to have a selection such a way that selection should be dependent. That means we need to understand what are the other circumstances that needs to be considered. So that is very important. Not just enough to have a boundary values just because the day field takes 1 to 31. So also important to understand the other aspects of dependency in terms of the variables. Similarly, let's define a clock. So we have a hour, minute, and seconds. So this again will have a dependency on each other. So we cannot go beyond 60. Once it reaches 60, it will go for the next one. Similarly, we go for 24, that is 24 hours. So we will have the rollover of 01 or 0. So likewise, we are going to have the issue of next date problem it is called. So we need to have thorough analysis of the boundary values in such cases. Important to have an understanding of the realistic inputs, how we are going to feed for the boundary value analysis. So we should not get stuck with the problems such as the next date problem. One more is there, is bit tricky. It's called a triangle problem. I'll just go through simplistically so that this also can be considered. So in fact, the first introduction of the triangle problem in 73 by Goenberger. There have been many more references to this problem as well, since making this one of the most popular example to be used in conjunction with testing literature. The triangle problem accepts three integers a, b, c as an input example, each of which are taken to be sides of a triangle. That means we have three sides, isosceles, equilateral, and scalens, whatever you want to call it. So these three inputs are sides of triangle. The values of these inputs are used to determine the type of the triangle. So what type of a triangle these three inputs are going to decide. So the triangle could be one of these like equilateral, or it could be isosceles or scalene, or it is not at all a triangle. So one of these is all factored based on the A, B and C. So for the inputs to be declared as being a triangle, these must satisfy the 6 conditions. So C1, C2, C3, C4, C5, C6. So we have 6 conditions well before we start the test. Why? Because first of all we need to define it's being a triangle or not. So to define that, we need to have a triangle defined with condition 1 as A greater than or equal to 1, less than or equal to 200, B less than or equal to 1, sorry, B greater than or equal to 1 and less than or equal to 200. Similarly, C between 1 and 200. Then we have other binding conditions. A should be less than B plus C, and B should be less than A plus C, C should be less than A plus B. So these conditions basically should satisfy in order to form the triangle. So otherwise this is never called as a triangle. So the type of the triangle, provided the conditions are met, is determined as follows. If all three sides are equal, the output is equilateral. Exactly one pair of sides is equal, the output is isosceles. If no pair of sides is equal, the output is scalene. After we define the triangle, we are going to have what type of a triangle it is. So we need to be very careful in choosing the test case also. We should be realistic in terms of the inputs. First of all, we need to define the criteria, how the requirement has been laid out. First we need to understand. That's what I am always emphasizing, that the tester has to have a good knowledge of the system under test. We should not get stuck within the testing and the testing aspects are not good in terms of test selection technique or test design technique, or the strategy is not good. First, having understood the system, we should design test cases such a way that the test is well behave in terms of executing and producing the output of the underneath embedded system. Okay, so to conclude on the equivalence partitioning and boundary value analysis, some important points that we need to see is these two are very effective test design techniques. We have to have mandatorily equivalence partitioning and boundary value analysis. We can find that boundary value analysis, if practiced correctly, is one of the most useful test case design methods. So boundary value analysis have to be correctly practiced or implemented, having considering all these issues and considering all the ranges, considering the different examples that we have seen, and the effectiveness of the boundary conditions, etc. So if it is correctly practiced, it will be very useful in terms of finding the bugs in the underneath embedded software. But as per the practices seen in the industry, it is often used ineffectively, as the testers often see it as so simple they misuse it. That means I believe that it's going to work, because when I plug it, I apply a power and it is behaving good, and I do little changes, still it is good. As a black box, I feel that system is good and gives a confidence. That's not the case. we should not consider that as a primary input. Rather, we should think in terms of having a bug, and I am going to challenge it in terms of bringing out all the issues. Or the tester would not have used it full potential. If you get a mobile or a handset or any telephone instrument, what basically user do as a user, he will plug it, he will switch it on, he will try to dial. So normal behavior. So he gets the content, that's fine. But instead of using it at its full potential, definitely he has to think out of the box in terms of testing it effectively. So for testing it effectively, he needs to understand what it is capable of, and what is the specification, what are the conditions that it can accept, what are the techniques that he can apply effectively and importantly. So that will bring out all the test effects which are having issues in terms of implementation. And this is more vital or important. Why? Because boundary value analysis will bring the effective way of bringing out the bugs. So BVA can provide a relatively simple and formal testing technique that can be very powerful when used correctly. That means we start formally with a simpler technique of identifying the equivalence classes, then identify the boundaries for each of the inputs that requirement or requirements identify, then select the tests based on these inputs, select the criteria, apply the tests and find the errors. When issues arises such as dependencies between variables or need of foresight into the system functionality, we can find boundary analysis as restrictive. That means, example, you take it as a next day problem. Realistic boundary value should allow for a user to give month as April and day as 31, but this is not a realistic input for an embedded system having a day as implemented functionality. So we cannot expect that. So that is a restriction for boundary value analysis. I mean, we should take a call in terms of boundary value analysis, uh, uh, taking out the such cases for such issues. So that is the conclusion of equivalence partitioning and boundary value analysis. I will have some of the glossary in embedded software testing added to each slide in different sessions. So we'll just go through that. Acceptance testing, we know that it's a formal testing from the user perspective. Actual result, the result behavior of a system as a result of processing the inputs. We know what is the behavior, the combination of input values and the preconditions, and the required response for a function of a system. So that is the behavior. The full specification of a function would normally comprise one or more behaviors. We know what is black box, testing test case selection based on the analysis of the specification of the component without reference to its internal knowledge or internal implementation details we will be found in the black box. And the white box, we know about the logic and the program flow. It is in alphabetical order, so that's why it is not listed at all, but we will revisit every one in the future sessions. So boundary value, an input value or output value which is on the boundary between equivalence classes or an incremental distance either side of the boundary. It could be upper, below, high or low, etc. So boundary value analysis is another test design technique as equivalence class for a component in which test cases are designed which include representatives of boundary values. Certification, a process of confirming that a system or component complies with specified requirements and is acceptable for operational use. So this is the IVMV responsibility. So we will talk about certification in future classes. Checklist is a list of questionnaires that can be answered yes or no. This is basically used by the support people for doing the IVMV, independent validation verification. Mostly this will be done as a toll gate before the product is tested and released. Mostly it will be done by the department such as QA. Okay, so we have an exercise question. Define the EP and the BVA test cases for the below example. The below example says the refrigerator, refrigerator has a red and green indicator. The optimal temperature in the refrigerator is between 3 and 8 degrees. If the temperature is within this interval, the green indicator is lit. Otherwise, the red indicator is lit. That means the indicator in the refrigerator will indicate a green if the temperature is between 3 and 8. If it is beyond that, it will show it as red. So we need to draw a equivalence partition as well as boundary value analysis test cases for the below. This is an exercise. So one more exercise. I think it's a continuation of the previous exercise. You can see a diagram of the temperature indicator. Develop a BVA for the example. Refrigerator has a red and a green indicator. The optimal temperature in the refrigerator is between 3 and 8. If the temperature is within this interval, the green indicator is lit. Same thing. The temperature range can be divided into 3 intervals. So I just give a few inputs. Accordingly, you can define the boundary value analysis and the equivalence partitioning. So from infinity, it could be minus any value, but without including the 3, which will result in red. Here down you can see 3 and below are red and 8 and above are red. Between 3 and 8 is green in the thermometer or the refrigerator temperature indicator. From 3 to 8 is green, but not including 8 to the higher value is red. So one more exercise. I think this exercise was given in the equivalence party. I will do an extension for this. So write equivalence class for the below. When the sensor temperature which is less than 10 degree or greater than 100 degree, it sets the value alert, else it sets the value normal. So write boundary class values for the above tolerance with a tolerance of plus or minus 1 degree. That means less than 10 degree plus or minus 1, greater than 100 degree plus or minus 1 should be applied for doing the boundary value analysis. Okay, so some of the embedded system testing words we will go through. We have defined all this in the previous sessions. We are going to have AV&B robustness, equivalence class, valid and invalid class, boundary analysis. Any new words we have learned today? We will see single problem, next date problem is okay, nominal, average, normal, we will add it. Okay, so we'll add nominal, normal, average, all this meaning the same. It is an type of input that is fed to the system. So that is about the boundary value analysis. So it's very important to learn boundary value analysis and equivalence partitioning, because the entire test design technique is founded with the help of these two techniques. We need to have this for the embedded software testing.